And we're recording as well? Okay, great. Just to remind you again, hello. We're recording the classes, so if you're uncomfortable speaking in the camera, you're not in the picture, but your voice might be on the recording. Okay, great. As you can see, also the screen is wider than it should be, and I'm not sure how to fix it, so we'll have to live with it. Luckily, your visual cortex is very good. It's very invariant to stretching, so this is not a problem. Okay, so we'll start out with some administrative things before we dive into the class. The first assignment will come out tonight or early tomorrow. It is due on January 20, so you have exactly 2 weeks. You will be writing a k-nearest neighbor classifier, a linear classifier, and a small 2-layer neural network. And you'll be writing the entirety of backpropagation algorithm for a 2-layer neural network. We'll cover all that material in the next 2 weeks. And warning, by the way, there are assignments from last year as well, and we're changing the assignments. So they will, please do not complete a 2015 assignment. That's something to be aware of. And for your computation, by the way, we'll be using Python and NumPy. And we'll also be offering terminal.com, which is basically these virtual machines in the cloud that you can use if you don't have a very good laptop and so on. I'll go into detail of that in a bit. I'd just like to point out that for the first assignment, we assume that you'll be relatively familiar with Python, and you'll be writing these optimized NumPy expressions where you're manipulating these matrices and vectors in very efficient forms. So for example, if you're seeing this code and it doesn't mean anything to you, then please have a look at our Python NumPy tutorial that is up on the website as well. It's written by Justin, and it's very good. And so go through that and familiarize yourself with the notation, because you'll be writing a lot of code that looks like this, where we're doing all these optimized operations so they're fast enough to run on a CPU. Now, in terms of terminal, basically what this amounts to is that we'll give you a link to the assignment. You'll go to a web page, and you'll see something like this. This is a virtual machine in the cloud that has been set up with all the dependencies of the assignment. They're all installed already. All the data is already there. And so you click on Launch a Machine. And this will basically bring you to something like this. This is running in your browser. And this is basically a thin layer on top of an AWS machine, a UI layer here. And so you have an iPad notebook and a little terminal, and you can go around. And this is just like a machine in the cloud. And so they have some CPU offerings, and they also have some GPU machines that you can use, and so on. You normally have to pay for terminal, but we'll be distributing credits to you. So you just email us to a specific TA that we'll decide in a bit. You email to a TA and you ask for money. We'll send you money. And we keep track of how much money we've sent to all the people, so you have to be responsible with the funds. So this is also an option for you to use if you like. OK. Any details about this? Yep, go ahead.
A quick question. You said that they have GPU units. Does that mean we can write Pycuda code, or is that not acceptable? You can write it if you like. It's not required for the assignment, but you can probably get that to run, yeah. OK, great. So I'm just going to dive into the lecture now. Today we'll be talking about image classification, and especially we'll start off on linear classifiers. So when we talk about image classification, the basic task is that we have some number of fixed categories, say a dog, cat, truck, plane, or so on. We get to decide what these are. And then the task really is to take an image, which is a giant grid of numbers, and we have to transform it to one of these labels. We have to bin it into one of the categories. This is the image classification problem. We'll spend most of our time talking about this one specifically. But if you'd like to do any other task in computer vision, such as object detection, image captioning, segmentation, or whatever else, you'll find that once you know about image classification and how that's done, everything else is just a tiny delta on top of it. So you'll be in a great position to do any of the other tasks. So it's really good for conceptual understanding, and we'll work through that as a specific example to simplify things in the beginning. Now, why is this problem hard? Just to give you an idea, the problem is what we refer to as a semantic gap. This image here is a giant grid of numbers. The way images are represented in the computer is that this is basically, say, roughly a 300 by 100 by 3 pixel array, so 3-dimensional array. And the 3 is for the 3 color channels, red, green, and blue. And so when you zoom in on a part of that image, it's basically a giant grid of numbers between 0 and 255. So that's what we have to work with. These numbers indicate the amount of brightness in all the 3 color channels at every single position in the image. And so the reason that image classification is difficult is when you think about what we have to work with, these like millions of numbers of that form, and having to classify things like cats, it quickly becomes apparent the complexity of the task. So for example, the camera can be rotated around this cat, and it can be zoomed in and out and rotated, shifted. The focal properties, intrinsics of that camera can be different. And think about what happens to the brightness values in this grid as you actually do all these transformations with the camera. They'll completely shift. All the patterns are changing, and we have to be robust to all of this. There's also many other challenges. For example, challenges of illumination. Here we have a long cat.
one cat. We actually have two of them, but you almost even can't see the other one. And so one cat is basically illuminated quite a bit, and the other is not. But you can still recognize two cats. And so think about, again, the brightness values on the level of the grid. And what happens to them as you change all the different lightings and all the possible lighting schemes that we can have in the world. We have to be robust to all of that. There's issues of deformation, many classes, lots of strange arrangements of all of these objects we'd like to recognize. So cats coming in very different poses. By the way, the slides, when I create them, they're quite dry. There's a lot of math and so on. So this is the only time I get to have fun. So that's why I just pile everything with cat pictures. So we have to be robust to all of these deformations. You can still recognize that there's a cat in all of these images despite its arrangement. There's problems of occlusion. So sometimes we might not see the full object, but you still recognize that that's a cat behind a curtain. That's a cat behind a water bottle. And there's also a cat there inside a couch, even though you're seeing just tiny pieces of this class, basically. There's problems of background clutter. So things can blend into the environment. We have to be robust to that. And there's also what we refer to as intra-class variation. So cat, actually, there's a huge amount of cats, just species. And so they can look different ways. We have to be robust to all of that. So I'd just like you to appreciate the complexity of the task. When you consider any one of these independently, it's difficult. But when you consider the full cross product of all these different things, and the fact that our algorithms have to work across all of that, it's actually quite amazing that anything works at all. In fact, not only does it work, but it works really, really well, almost at human accuracy. We can recognize thousands of categories like this, and we can do that in a few dozen milliseconds with the current technology. And so that's what you'll learn about in this class. So what does an image classifier look like? Basically, we're taking this 3D array of pixel values. We'd like to produce a class label. And what I'd like you to notice is that there's no obvious way of actually encoding any of these classifiers, right? There's no simple algorithm. Like, say you're taking an algorithms class in your early computer science curriculum. You're writing bubble sort, or you're writing something else to do any particular task. You can intuit all the possible steps, and you can enumerate them and list them and play with it and analyze it. But here, there's no algorithm for detecting a cat under all these variations, so it's extremely difficult to think about how you'd actually write that up. What is the sequence of operations you would do on an arbitrary image to detect a cat? That's not to say that people haven't tried, especially in the early days of computer vision. There were these explicit approaches, as I'd like to call them, where you think about, OK, a cat, say, we'd like to maybe look for little earpieces. So what we'll do is we'll detect all the edges. We'll trace out edges. We'll classify the different shapes of edges and their junctions. We'll create libraries of these, and we'll try to find their arrangements. And if we ever see anything ear-like, then we'll detect a cat. Or if we see any particular texture of some particular frequencies, we'll detect a cat. And so you can come up with some rules. But the problem is that once I tell you, OK, I'd like to actually recognize a boat now, or a person, then you have to go back to the drawing board, and you have to be like, OK, what makes a boat? Exactly what's the arrangement of edges, right? It's a completely unscalable approach to classification. And so the approach we're adopting in this class, and the approach that works much better, is the data-driven approach that we like in the framework of machine learning. And just to point out that in these days, actually, in the early days, they did not have the luxury of using data, because at this point in time, you're taking grayscale images of very low resolution. You have 5 images, and you're trying to recognize things. It's obviously not going to work. But with the availability of internet, huge amount of data, I can search, for example, for cat on Google, and I get lots of cats everywhere. And we know that these are cats based on the surrounding text in the web pages. And so that gives us lots of data. So the way that this now looks like is that we have a training phase where you give me lots of training examples of cats, and you tell me that they're cats. And you give me lots of examples of any type of other category you're interested in. I go away and I train a model. A model is a class. And I can then use that model to actually classify new test data. So when I'm given a new image, I can look at my training data, and I can do something with this based on just a pattern matching and statistics and so on. So as a simple first example we'll work with in this framework, consider the nearest neighbor classifier. The way nearest neighbor classifier works is that effectively we're given this giant training set. What we'll do at training time is we'll just remember all of the training data. So I have all the training data. I just put it here, and I remember it. Now, when you give me a test image, what we'll do is we'll compare that test image to every single one of the images we saw in the training data, and we'll just transfer the label over. So I'll just look through all the images. We'll work with specific case. As I go through this, I'd like to be as concrete as possible. So we'll work with a specific case of something called CFAR10 dataset. The CFAR10 dataset has 10 labels. These are the labels. There are 50,000 training images that you have access to. And then there's a test set of 10,000 images where we're going to evaluate how well the classifier is working. And these images are quite tiny. They're just a little toy data set of 32 by 32 little thumbnail images. So the way nearest neighbor classifier would work is we take all this training data that's given to us, 50,000 images. Now at test time, suppose we have these 10 different examples here. These are test images along the first column here. What we'll do is we'll look up nearest neighbors in the training set of things that are most similar to every one of those images independently. So there you see a ranked list of images that are most similar to in the training data to any one of those 10, to every one of those test images over there. So in the first row, we see that there's a truck, I think, as a test image. And there's quite a few images that look similar to it. We'll see how exactly we define similarity in a bit. But you can see that the first retrieved result is, in fact, a horse, not a truck. And that's because of just the arrangement of the blue sky that was throwing that off. So you can see that this will not probably work very well. Now, how do we define the distance metric? How do we actually do the comparison? There are several ways. One of the simplest ways might be a Manhattan distance. So an L1 distance or a Manhattan distance, I'll use the two terms interchangeably. Simply what it does is you have a test image you're interested in classifying, and consider one single training image that we want to compare this image to. Basically what we'll do is we'll element-wise compare all the pixel values. So we'll form the absolute value differences, and then we just add all of it up. So we're just looking at every single pixel position. We're subtracting it off and seeing what the differences are at every single spatial position, adding it all up, and that's our similarity. So these two images are 456 different. Okay? So we'll get a 0 if we have identical images here. Just to show you code specifically, the way this would look like, this is a full implementation of a nearest neighbor classifier in NumPy and Python, where I filled in the actual body of the two methods that I talked about. And basically what we do here at training time is we're given this data set, X, the images, and Y, which usually denote the labels. So we're giving images and labels. All we do is just assign to the class instance methods. So we just remember the data. Nothing is being done. At predict time, though, what we're doing here is we're getting new test set of images X. And I'm not going to go through full details, but you can see that there's a for loop over every single test image independently. We're getting the distances to every single training image. And notice that that's only a single line of vectorized Python code. So in a single line of code, we're comparing that test image to every single training image in the database, and we're computing this distance in a previous slide in a single line. Okay? So that's vectorized code. We didn't have to expand out all those for loops that are involved in processing this distance. And then we compute the instance that is closest. So we're getting the min index. So that's the index of the training example that has the lowest distance. And then we're just predicting for this image the label of whatever was nearest. Okay? So here's a question for you in terms of the nearest neighbor classifier. How does its speed depend on the training data size? What happens is I scale up the training data. It's slower, okay? Yes, it's in fact linearly slower, right? Because if I have to compare to every single training example independently. So it's a linear slowdown. And you'll notice actually as we go through the class is that this is actually backwards. Because what we really care about in most practical applications is we care about the test time performance of these classifiers. That means that we want this classifier to be very efficient at test time. And so there's this trade-off between really how much compute do we put in the train method and how much compute do we put in a test method. A nearest neighbor is instant at train, but then it's expensive at test. And as we'll see soon, ComNet's actually flipped this completely the other way around. We'll see that we do a huge amount of compute at train time. We'll be training a convolutional neural network. But the test time performance will be super efficient. In fact, it will be constant amount of compute. For every single test image, we'll do constant amount of computation. No matter if you have a million, billion, or trillion training images. I'd like to have a trillion training images. No matter how large your training data set is, we'll do a constant compute to classify any single testing example. So that's very nice, practically speaking. Now, I'll just like to point out that there are ways of speeding up nearest neighbor classifiers. There's these approximate nearest neighbor methods. Flan is an example library that people use often in practice that allow you to speed up this process of nearest neighbor matching. But that's just a side note. OK. So let's go back to the design of the nearest neighbor classifier. We saw that we've defined this distance. And I've arbitrarily chosen to show you the Manhattan distance, which compares the difference of the absolute values. There's, in fact, many ways you can formulate a distance metric. And so there's many different choices of exactly how we do this comparison. Another choice that people like to use in practice is what we call the Euclidean or L2 distance, which instead sums up the differences in the sums of squares of these differences between images. And so this choice, what happened there? Did someone push a button over there in the back? OK, thank you. So this choice of how exactly we compute a distance, it's a discrete choice that we have control over. That's something we call the hyperparameter. It's not really obvious how you set it. It's a hyperparameter. We have to decide later on exactly how to set this somehow. Another sort of hyperparameter that I'll talk about in context of nearest neighbor classifier is when we generalize nearest neighbor to what we call a k-nearest neighbor classifier. So in a k-nearest neighbor classifier, instead of retrieving for every test image the single nearest training example, we'll in fact retrieve several nearest examples, and we'll have them do a majority vote over the classes to actually classify every test instance. So say a 5 nearest neighbor, we would be retrieving the 5 most similar images in the training data and doing a majority vote of the labels. Here's a simple 2-dimensional data set to illustrate the point. So here we have a 3-class data set in 2D. And here I'm drawing what we call decision regions of this nearest neighbor classifier here. What this refers to is we're showing the training data over there, and we're coloring the entire 2D plane by what class this nearest neighbor classifier would assign at every single point. Suppose you had a test example somewhere here, then this is just saying that this would have been classified as blue class based on the nearest neighbor. You can, for example, note that here is a point that is a green point inside the blue cluster, and it has its own little region of influence where it would have classified a lot of test points around it as green, because if any point fell there, then that green point would have been the nearest neighbor. Now, when you move to higher numbers for k, such as 5 nearest neighbor classifier, what you find is that the boundaries start to smooth out. It's kind of this nice effect where even if there's this one point kind of randomly as a noise, an outlier in the blue cluster, it's actually not influencing the predictions too much because we're always retrieving 5 nearest neighbors, and so they get to overwhelm the green point. So in practice, you'll find that usually k nearest neighbor classifiers offer better performance at test time. Now, but again, the choice of k is, again, a hyperparameter. Right? So I'll come back to this in a bit. Just to show you an example of what this would look like, here I'm retrieving 10 most similar examples. They're ranked by their distance. And I would actually do a majority vote over these training examples here to classify every test example here. OK. So let's do a bit of questions here, just for fun. Consider what is the accuracy of the nearest neighbor classifier on the training data when we're using Euclidean distance. So suppose our test set is exactly the training data, and we're trying to find the accuracy. In other words, how often would we get the correct answer?
100%.
100%? Good. Why? OK, among the murmurs, yeah, that's correct. So we'll always find a training example exactly on top of that test, which has 0 distance, and then its value will be transferred over. Good. What if we're using the Manhattan distance instead? So the Manhattan distance doesn't use sum of squares, it uses sum of absolute values of differences.
Wouldn't it be the same?
It would. It's just a trick question. It would be the same. OK, good. So we're paying attention here. OK, what is the accuracy of the k nearest neighbor classifier in the training data? Then say k was 5. Is it 100%?
No.
Not necessarily, right? Good. Because basically the points around you could overwhelm you even if your best example is actually of a different class. OK, good. So we've discussed 2 choices of different here hyperparameters. We have the distance metric. It's a hyperparameter. And this k, we're not sure how to set it. Should it be 1, 2, 3, 10, and so on. So we're not exactly sure how to set these. In fact, they're problem dependent. You'll find that you can't find a consistently best choice for these hyperparameters. In some applications, some k's might work better than other applications. So we're not really sure how to set this. So here's an idea. We have to basically try out lots of different hyperparameters. So what I'm going to do is I'm going to take my train data, and then I'm just going to try out lots of different hyperparameters. So I have my test data, and I try out k equals 1, 2, 3, 4, 5, 6, 20, 100. I try out all the different distance metrics, and whatever works best, that's what I'll take. So that will work very well, right?
No.
It won't work very well? Why is this not a good idea?
Because you will fail to generalize on unseen data.
OK. So basically, yes. So test data is your proxy for your generalization of your algorithm. You should not test the test data. In fact, you should forget that you ever have test data. So once you're given your data set, always set aside the test data, pretend you don't have it. That's telling you how well your algorithm is generalizing to unseen data points. And this is important because you're trying to develop your algorithm, and then you're hoping to eventually deploy it in some setting. And you'd like to have an understanding of exactly how well do I expect this to work in practice. right? And so you'll see that, for example, sometimes you can perform very, very well in training data, but not generalize very well to test data when you're overfitting and so on. And a lot of this, by the way, 229 is a requirement for this class. So you should be quite familiar with this. This is to most extent, this is kind of more of a review for you. But basically, this test data is use it very sparingly, forget that you have it. Instead, what we do is we separate our training data into what we call folds. So we separate, say, we use a 5-fold validation. So we use 20% of the training data as an imagined test set data. And then we only train on part of it, and we test out the choices of hyperparameters on this validation set. So I'm going to train on my 4 folds and try out all the different case and all the different distance metrics and whatever else. If you're using approximate nearest neighbor, you have many other choices. You try it out, see what works best on that validation data. If you're feeling uncomfortable because you have very few training data points, people also sometimes use cross-validation, where you actually iterate the choice of your test or validation fold across these choices. So I'll first use 1 to 4 for my training and try out on 5. And then I cycle the choice of the validation fold across all the 5 choices. And I look at what works best across all the possible choices of my test fold. And then I just take whatever works best across all the possible scenarios. Okay? That's referred to as a cross-validation set, cross-validation. So in practice, the way this would look like, say we're cross-validating for K for a nearest neighbor classifier, is we are trying out different values of K. And this is our performance across 5 choices of the fold. So you can see that for every single K, we have 5 data points there. And then this is the accuracy, so high is good. And I'm plotting a line through the mean, and I'm also showing the bars for the standard deviations. So what we see here is that the performance goes up across these validation folds as you go up, but at some point it starts to decay. So for this particular data set, it seems that K equal to 7 is the best choice. So that's what I'll use. I'll do this for all my hyperparameters, also for distance metric and so on. I do my cross-validation. I find the best hyperparameters. I set them. I fix them. Then I evaluate a single time on the test set. And whatever number I get, that's what I report as an accuracy of a k-nearest neighbor classifier on this data set. That's what goes into a paper. That's what goes into your final report, and so on. That's the final generalization result of what you've done. OK? Any questions about this? Yep.
So the reason that happens with K is that because large K gives you high bias?
I would be careful with that terminology, but basically, it's about the statistics of the distribution of these data points in your label, in your data space. And so sometimes it's basically hard to say. Like you get, where's this picture? You see roughly what's happening is you get more clunkiness in more Ks. And it just depends on how clunky your data set is. That's really what it comes down to, is how blobby is it, or how specific is it? I know that's a very hand-wavy answer, but that's roughly what that comes down to. So different data sets will have different clunkiness. Yeah?
How do you deal with skewed data sets?
Skewed data sets. So what is that referring to?
A lot more of one class than the other class.
So that's a technical question that I maybe don't want to get into right now, but we will address that later in the class probably. Oh yeah, go ahead.
Shouldn't tuning hyperparameters data set specific be considered achieving?
No, not at all, because your hyperparameters are just choices. You're not sure how to set them, and different data sets will require different choices, and you need to see what works best. In fact, when you try out different algorithms, because you're not sure what's going to work best on your data, the choice of your algorithm is also kind of like a hyperparameter. So you're just not sure what works. You're not different. Approaches will give you different generalization boundaries. They will look different, and some data sets have different structure than others, so some things work better than others. And you have to just try it out. OK, cool. I just like to point out that k-nearest neighbors is, no one basically uses this. So I'm just going through this just to get you used to this approach of really how this works with training, test splits, and so on. The reason this is never used is because, first of all, it's very inefficient. But second of all, distance metrics on images, which are very high-dimensional objects, they act in very unnatural, unintuitive ways. So here what I've done is we're taking an original image, and I change it in 3 different ways. But all these 3 different images here have actually the exact same distance to this one in an L2 Euclidean sense. And so just think about it. This one here is slightly shifted to the left. It's basically cropped slightly. And its distances here are completely different because these pixels are not matching up exactly, and it's all introducing all these errors, and you're getting a distance.
This one is slightly darkened, so you get a small delta across all spatial locations. And this one is untouched, so you get 0 distance errors across everywhere, except for in those positions over there. And that is taking out critical pieces of the image, and it doesn't, the nearest neighbor classifier would not be able to really tell a difference between these settings, because it's based on these distances that don't really work very well in this case. So very unintuitive things happen when you try to throw distances on very high dimensional objects. That's partly why we don't use this. Okay. So in summary, so far, we're looking at image classification as a specific case, and we'll go into different settings later in the class. I've introduced the nearest neighbor classifier and the idea of having different splits of your data. And we have these hyperparameters that we need to pick, and we use cross-validation for this usually. Most of the time, people don't actually use entire cross-validation. They just have a single validation set, and they try out on the validation set whatever works best in terms of the hyperparameters. And once you get the best hyperparameters, you evaluate a single time on a test set. Okay. So I'm going to go into linear classification in a bit. Any questions at this point? Otherwise, okay, great. Okay. So we're going to look at linear classification. This is a point where we are starting to work towards convolutional neural networks. So there will be a series of lectures. We'll start with linear classification that will build up to an entire convolutional network analyzing an image. Now, I'd just like to say that we've motivated the class yesterday from a task-specific view. So this class is a computer vision class. We're interested in giving machines sight. Another way to motivate this class would be from a model-based point of view, in the sense that we're giving you guys, we're teaching you guys about deep learning and neural networks. These are wonderful algorithms that you can apply to many different data domains, not just vision. So in particular, over the last few years, we saw that neural networks can not only see, that's what you'll learn a lot about in this class, but they can also hear. They're used quite a bit in speech recognition now. So when you talk to your phone, that's now a deep neural network. They can also do machine translation. So here you're feeding a neural network a set of words one by one in English, and the neural network produces the translation in French or whatever else target language you have. They can also perform control. So we've seen neural network applications in robots, manipulation, in playing of Atari games. So these neural networks learn how to play Atari games just by seeing the raw pixels of the screen. And we've seen neural networks be very successful in a variety of domains, and even more than I put here. And we're uncertain exactly where this will take us. And then I'd like to also say that we're exploring ways for neural networks to think, but this is very hand-wavy. It's just wishful thinking. But there's some hints that maybe they can do that as well. Now, neural networks are very nice because they're just fun, modular things to play with. When I think about working with neural networks, this picture comes to mind for me. Here we have a neural networks practitioner, and she's building what looks to be a roughly 10-layer convolutional neural network at this point. And so these are very fun. Really, the best way to think about playing with neural networks is like Lego blocks. You'll see that we're building these little function pieces, these Lego blocks that we can stack together to create entire architectures. And they very easily talk to each other. And so we can just create these modules and stack them together and play with this very easily. One work that I think exemplifies this is my own work on image captioning from roughly a year ago. So here the task was, you take an image and you're trying to get the neural network to produce a sentence description of the image. So for example, in the top left, these are test set results. The neural network would say that this is a man in black shirt is playing guitar, or a construction worker in orange safety vest is working on the road, and so on. So the neural network can look at the image and create this description of every single image. And when you go to the details of this model, the way this works is we're taking a convolutional neural network, which we know. So there's two modules here in this system diagram for image captioning model. We're taking a convolutional neural network, which we know can see, and we're taking a recurrent neural network, which we know is very good at modeling sequences, in this case, sequences of words that will be describing the image. And then just as if we were playing with Legos, we take those two pieces and we stick them together. That's corresponding to this arrow here in between the two modules. And these networks learn to talk to each other